Welcome everybody. This is our Tech Tuesday, and today we are going to be focusing on electrical energy monitoring strategies. My name is Greg Hoyer, and over the years, in the last 5 to 10 years especially, the term big data has been disseminated from our industry, and we see often the analytic side of energy monitoring. That is, we're looking at the information that's coming into the system via either a kW pulse meter or an E-Mon meter or a Dent meter or something like that. And the information is stored and not much is being done with it. And then over the years, I've thought to myself, well, we used to do energy strategies based on what the energy of the building was doing. Everything that I'm talking about today is basically centered around the inbound power to the building, where your utility meter would be. But it doesn't necessarily have to relate to the entire building. You can do everything that we are going to talk about today on a particular piece of equipment or on a sub-meter zone or on a particular wing of the building, depending on the electrical distribution. So that's kind of where I wanted to go with the presentation today. It's not necessarily, I'm not going to talk specifically about electrical meters. I'm going to talk, what do we do with the information that these meters or these kW pulse inputs provide us? So in doing so, the objectives that I wanted to hit today were some critical electrical terms. These are terms that all of us use all the time, and maybe a little bit of in-depth discussion on what they mean might reveal where this stuff is coming from, where the terms that we're going to be talking about. And I wanted to show some common ways to monitor and accumulate the electrical data. As I said, the meters, kW, pulse, contacts that we get from our utilities. And now that we have accumulated the information, we're deriving the information, what do we do with this information other than storing it to an analytical database and comparing it to what we did last year? There are so many variables that are associated with energy that may affect what it is we're looking at, and it's just a bunch of information, and it may not mean anything from year to year or from month to month, but the things that we're going to talk about today relate to what do we do with control of our building as it relates to energy. And then the last thing I wanted to pick up on was some of the pitfalls that are associated with energy meters and people don't consider when things are installed. So we've all heard the term voltage, right? And it comes from an Italian physicist, Alessandro Volta. Okay, this guy invented the voltaic pile, which is today's, it's the forerunner of today's battery. And I consider voltage like pressure in an electrical circuit's power source that pushes the charged electrons or current through a conducting loop, enabling them to do work such as illuminating a light. So voltage is potential energy, and it's analogous to water pressure. And I put together a slide that kind of shows the relationship to electricity with regard to fluid dynamics, okay? The characteristics of voltage are like that of water flowing through pipes, right? It's sometimes used to explain electric circuits to a closed circuit water filled with pipes that's pressurized by a pump, okay? So current is the rate of flow that's measured in amps, okay? Ohms, which is a measure of resistance, is analogous to the pipe size of our water, water that's flowing. The current is proportional to the diameter of the pipe or the amount of water flowing at that pressure. Okay, voltage is an expression of the available energy per unit charge with drives of electric current around a closed circuit in a direct DC electrical circuit. So if we increase the resistance comparable to decreasing the pipe size in a water circuit, we'll proportionally decrease the current or water flow in the water flow in the water circuit, which is driven through the circuit by voltage, which is compared to hydraulic pressure in a water circuit. So what does that mean? Okay. I put this slide together and it shows the relationship between voltage and current. And it's something that George Ohm wrote about in 1827. Everybody's heard of Ohm's law. That came later, but his papers were originally posted in 1827. So there's these other physicists, Hagen, Poussel, French guys, that related the same equation that George Ohm came up with to fluid dynamics. So they're directly, it's a relationship that shows through fluid dynamics what's happening in an electrical circuit. So flow is equal to delta P over R, and in the Ohm's law, current is equal to the change in voltage over resistance. And that's essentially what this is, this diagram showing us. So I'm talking about these terms because it gets us to what we really need to understand as it relates to energy usage. So I started looking into some of these terms, and it's sort of like some cobwebs off of what these things actually mean. Now, you know, and I can read this thing to you, but basically, amp, short for an ampere, is a unit of electrical current, which the international standards defines as a term of other base units by measuring the electromagnetic force between electrical conductors carrying electrical current. So a lot of this stuff is defined here on the screen and on these slides, and it's good reference material to go back to. I don't want to sit here and read a PowerPoint presentation everybody can read, but an ampere is essentially a unit of electrical current. It's the strength of a current of electricity expressed in amperes, right? So that gets us to watts. Okay, watt is a measure of power, and that's the crux of this entire discussion today. 1 watt is a rate of work that's done by 1 ampere of current flows through an electrical potential difference, which is a volt, and can be expressed as 1 watt equals 1 volt times 1 amp. Very simple. So watts amps, watts is equal to volts times amps, okay? Sorry, I'm getting ahead of myself. You can reorder things to come up with the other parts of the equation. For volts, you can divide watts by amps, and amps can be watts divided by volts. So we come up with this unit of measure of power, which is watts. So we get into now what everybody is more familiar with is a kilowatt. It's expressed as kW, and it's equal to 1,000 watts, 10 to the third power. It's usually a term that's associated with the output of power engines for motors, tools, machines, and heaters. It's also commonly used to express an electromagnetic power output of broadcast radio and television transmitters. And it's also important to recognize that a kilowatt is approximately 1.34 horsepower. So I got this international standards thing on the right here, and it talks about the different measurements of watts in multiples and in submultiples. So a kilowatt, which is 1,000 watts, and is 10 to the third. A megawatt, everybody knows about a megawatt. You've heard them related in like generators and stuff like that. That's 1,000,000 watts. A gigawatt is 1,000,000,000 watts, etc., and so forth. It gets us to kilowatt hours, and it's a composite unit of energy equal to 1 kilowatt of power sustained for 1 hour. So a kilowatt is an instantaneous amount of energy or power being used. Kilowatt hour takes into consideration time as well as instantaneous power. It's equivalent to 3,600 kilojoules. I'm not sure if that means anything to anybody, but kilowatt hour is commonly used for billing and energy delivered to consumers by electric utilities. Everybody's heard of a kilowatt hour. It's on all of our electric bills, and the buildings that our contractors take control of in the building automation field know this term pretty well. And it's kind of it's a composite of instantaneous power over time. So the electrical costs of running a building is calculated by multiplying the building's power consumption in kilowatts by the time in hours, as I just said. And then all of that is multiplied by the price per kilowatt. It's important to note that the unit price of electricity charged by utilities companies may depend on the customer's consumption over time. The consumption profile is usually referred to as demand. That is pretty important stuff right there. So I have an example that I was going to talk about here, but a little bit more about demand. Buildings that are being supplied with electrical power are not always at the most advantageous rates. Major part of the electricity bill for commercial facilities is not based upon the number of kilowatt hours that is consumed, but it's based on the highest demand peak reached during that month. So what does that mean? That means that we have our kilowatt hour rate that the utility charges us for, but that rate is based upon usually, and it differs because it's a complicated algorithm that utilities use, but it's usually, that rate is usually based upon the highest amount of energy in a single instance that facility uses, and that's referred to as your peak demand. So if you are running your air conditioners and it's the middle of July and your building is consuming all of this energy in an instance, that is the rate usually that a facility will be charged for the entire year. So if we have steam boilers or gas boilers in the wintertime, we're still being charged our kilowatt hours times that maximum rate that we used in the middle of the summertime. So commercial and industrial customers, and even some residential now, get types of charges. So as I said, we get our kilowatt hours, and the other is our demand charged. And that's measured in kilowatts. That's instantaneous, okay? The kilowatt hour portion of the bill is the total amount of energy that is consumed for the billing cycle. And in most cases, it's around 30 days. So if we think of kilowatt hours as the usage over time, demand, on the other hand, is the rate of the energy that the energy is consumed. Utility companies must be able to generate and provide each customer with their individual requirements. So if you take into consideration two customers, suppose customer number one has 10 100-watt light bulbs, and the other customer has one 100-watt light bulb, okay? Now, let's suppose that the first customer with the 10 100-watt light bulbs has a warehouse and only comes in once a month for 1 hour to check on things. If these 10 100-watt light bulbs run for 1 hour, they consume 1,000 watt hours, or 1 kilowatt, right, for the month. So that's 10 times 100 equals 1,000 watts divided by 1,000, which is 1 kilowatt hour. Now, the second customer has one 100-watt light bulb, and let's say he has baby chickens, and he turns the light stays on for the entire month, that one 100-watt bulb. So he needs to keep the light running the entire month, the one bulb. So the bulb, that one bulb would consume 72,000 watt hours, or 72 kilowatt hours. So that works out to 100 times 24. That's our one bulb times 24 hours times 30 days, which is 72,000 watts divided by 1,000 equals 72 kilowatt hours. So that's all well and good. But where does the demand come into play? So the first customer, the guy that only comes in for an hour a month, has 10 100-watt light bulbs. So when he turns those 10 light bulbs on, he's using a much greater demand than the guy that has one light bulb running it all month long. And the utility companies have to be able to provide for that demand when the guy comes in and turns on those 100-watt light bulbs, all 10 of them, for an hour. So he needs a bigger transformer and more amperage. These equations that I talked about in the beginning come into play. So the first customer in the example would require a larger transformer based on the calculations that I just threw out there. His demand would be 1 kilowatt, right? So the demand for the second customer would be 0.01 kilowatts. I'm sorry, 0.1 kilowatts. We convert this to amps, right? We showed that equation earlier. So amps equals watts divided by volts. If we have a 240 volt lighting circuit, we would divide the 1,000 by 240 for the first guy, and he would need 4.17 amps. And the second guy has 100 watts divided by 240 volts, which is 0.417 amps. So you can see that the first guy, in this very, very simple example, with the 10 100-watt light bulbs, he's going to need a larger transformer. Now, this is a very, very simple example, but you can see why the utilities have to charge the end users with a higher rate. It's not the same. It's not an apple for an apple. The guy that's running the 100-watt light all month is using less of a demand than the guy that has 10 100-watt light bulbs that's running them for an hour. The reason that the demand charges are there is to help the utilities offset the costs for the infrastructure that it has been built to supply each customer, such as larger transformers. Another reason that the utility has to demand charges because the utility pays a higher demand charge when it purchases electricity. It also causes them to run their generator plants more to keep up with demand. Like in the summertime, we have these blackouts that happen or brownouts that happen. And that is because the demand of the customers exceeds the generation capacity of the utility. Those are two reasons there that the electrical demand rate is charged usually on commercial customers. So when we calculate demand, it's usually done one of two ways. It's either in a block or a rolling scale. There are different demand intervals that also come into play. So you have a 5, 10, 15, or 30 minute. 30 is probably the most common that everybody sees. And what happens is in the block demand, it breaks down each day into whatever the interval is. And let's say it's 30. If it's 30 minutes, that means the meter begins to calculate the highest demand over a 30-minute interval. And that at the end of the interval, it starts all over again. So let's say at 10 o'clock in the morning, it starts counting. And every time we get a kilowatt, it registers on the meter. That could come in as a pulse. That could come in as on our meters that we sell. That rate of which the kilowatts are consumed in the building begins to increase based upon how much equipment is being used. At the end of that half an hour interval, it starts all over again. So you reset the clock, or you reset the time, the counter, I should say, and it starts counting all over again. So, as I said in the beginning, the highest half an hour, and I'm going to just make this very, very simple terms. So, the highest half an hour of energy usage over the entire year is what your rate is. Now, the other way that you can do things is called a sliding window demand, or it's called also known as a rolling demand. Then the block uses a fixed scale, whereas a rolling demand uses a sliding scale. And the most important thing to consider with the sliding window or the rolling scale is that it offers better response than a single fixed interval. And that may or may not make a lick of difference depending on how much energy the customer is using. But very often we don't know where that 30 minutes begins and where that 30-minute ends, that the utility company or the meter on the building starts and ends. That's the problem with the block, is we have no idea when that half an hour, like I said, it was started at 9 o'clock. Well, what if it started at 9:06 and it ended at 9:36? Okay, so we don't know where that half an hour is. So the problem with the block demand, although I think it's probably the most common means that utilities use. Now, we have a big country and we have a lot of utilities, and everybody has their own way. And as I said, it's kind of complicated. So the best thing that we do in the energy saving aspect of this thing is we sort of essentially we take a half an hour or a 15-minute sliding window, and we may or may not be in the scale of the utility, but we're still counting the pulses or the kilowatts that come in that interval. And if we have our own sliding window and we say, hey, in our scale, we used, 1,000 kilowatts in our worst half an hour, that is the objective to keep below. So I've been talking about all this demand stuff, and the object here is to keep our highest demand, whatever that is, whether it's a 30-minute block or whether it's a rolling demand. The objective here is to keep that demand for the highest usage, instantaneous usage, as low as we possibly can. That's the whole object of this conversation. as I said, in Philadelphia, Pico has a KYZ contact that they used to offer, and it told you every single pulse was equivalent to 1.2 kilowatt or 1 kilowatt. Let's make it real simple. So Pico would provide us with whatever was programmed at the meter, and every time that the a kilowatt was used, it gave us a dry contact. Now, we could use a totalization input from a controller, and here I've used a controller, but it could be a Johnson controller. It could be, whoever control systems out there, as long as they can have a totalization input for a counter input. We can count pulses and generate our own sliding window demand rate that way. Most common that we see is through the use of smart meters. Brody Precision sells a number of different vendors of meters. And the E-Mon, which is now owned by Honeywell, comes in a large amount of different types of controllers for different applications. I started out here with the 30 smart meter, and this particular guy wants to be integrated with an RS-485 communication protocol. It has, this particular one here does the EZ7, which is the E-Mon protocol, works with their software, and I'm not even sure if it's still available anymore. Maybe the sales guys could chime in and let me know if the EZ7 is still available. I know it was in the past, but it may have been phased out when Honeywell purchased E-Mon. But certainly Modbus RTU, which is the 485 communication, or the BACnet MSTP. And this would integrate to our Niagara-based control system. And we could do our information gathering through this meter into our Jace and then disseminate that through our different control system, either controllers or pieces of equipment that are controlled via integration through BACnet or Modbus or LAN or whatever. Most of the meters, okay, George is telling me that the EZ7 is still available on a couple of different meters. All the meters that I'm going to show here, I'm starting out with the lower end. These are not sub-meters, and again, they're the E-Mon and the Dent that I'm going to show, and ABB and Schneider, which I believe we also sell at Brody Precision. I'm not sure we sell ABB, although we're a distributor, but I don't know if we can get their meters. Most all meters that we can do an integration to will provide us with the pulse connect that I spoke of, or an integration where we can read directly what our kilowatt is at any given moment. Real-time loaded kilowatts says right there. Now, anybody that's hooked up a meter knows that we put our CTs around our three-phase or our single-phase legs of power. That's our amperage rate. And it also requires us to connect up to each phase with voltage. And this goes back to the beginning of this presentation where I talked about the relationship between amps and volts. If you give me those two values, I can calculate. And when I can calculate watts, I can calculate kilowatts. And when I can calculate kilowatts, I can calculate kilowatt hours. The beauty of these meters is that's done for you. So there's less software from the programming standpoint that has to be done. The next meter is the 3400 E-Mon, and you can see that has dual protocol. And I believe this particular meter also offers Ethernet, yes. And it does, let's see. This is just Ethernet. I don't think it does 485. So we can do, on this particular flavor, we can do the EZ7 protocol, Modbus, BACnet, MSTP. So yes, it does do for RS485, certain models of this 3400 smart meters. So there's a number of different protocols that, as you spend more money on the higher class of meters, it gives you more stuff that you can pull out of your energy information. Amps per phase, volts per phase. Again, real-time load in kilowatts, which is important to our discussion. There are things that can be done with this information as far as shutting down pieces of equipment. If your loads are in balance for whatever reason, you lost a phase that came in from the utility, you can do emergency shutdowns on equipment and save your customer a ton of money on burnt up motors of some sort. So this information is all very, very good to use from a safety and a shutdown standpoint. The next class of meter is the 5000 submeter. Again, dual protocol. Does 485 as well as Ethernet. I see it has a LAN flavor for those of us that are still using LAN. But again, you can see that the basic information that comes out of this thing, while it gives you more and more features, the more money you spend on this stuff, the basic stuff that we need for this information, from this meter, is in the least expensive meter as well. It gives us the real-time kilowatts, and it gives us a kilowatt hour with a peak of date and time. They all do that. And there are displays with these meters that you can walk up to and read. And so one of the things that I often bring up with customers that are purchasing meters from us, this is good information for analytics, but it's also good for control and demand limiting and some of the other strategies we're going to talk about. But when you compare what the building's utility meters and what the building is getting charged with, and compare it to one of the meters that is installed slightly upstream, they may not match. And the discussion that I've had in the past is, so what are you going to do? Challenge the utility? And most people just pay the bill. They don't challenge the utility at all. But I have had a couple of contractors that go in and say, hey, we're not reading what you're reading, and they've got an adjustment on their utility. So it has worked to keep the utility in check. Some of the other manufacturers of meters is Dent. We sell Dent meters as well at Brody Precision. This is the low end. And you can see this produces a 485 protocol. And let's see here. What does this thing do? This thing is going to do... crap, I thought it told me on this particular... I think it's MSTP and Modbus. George also said that we also sell Phoenix. Phoenix sells meters as well. So the point of these slides is essentially to point out that, yeah, Brody Precision sells these meters. These are things, these are tools that we're going to use to get to the end game. I would recommend that our customers contact their sales rep for the best application that suits their needs. And those guys can access Frank and I if need be. I'm just bringing up E-Mon or Honeywell and the Dent for the purposes of these slides. This particular meter made by Dent is going to be MSTP or RS485, which is a Modbus RTU. And you'll see, if you look closely on the meter, it talks about the exact same thing Honeywell has as well. I mean, you have your CT inputs, your current transformers that get wrapped around each phase, and then you have your voltage, line 1, line 2, and line 3 that's shown here on the left. That's kind of the commonality that you'll see from meter to meter, because we need voltage and we need amperage to calculate kilowatts. All meters are going to contain the same sort of basic wired inputs. And the meters themselves will differ based upon the features that they provide. But as you can see, it's going to tell us, each meter here will tell us volts, amps, kilowatts, etc. There's lots of parameters that these things will come out of, that will come out of these things via the protocols that you match up with. Moving up the scale in the Dent world, this is the 12 HD, and I believe this is an Ethernet flavor. This also provides pulsed points back to a building automation system if you need to. Again, it will give us the measurements that you can see here are greatly increased based on the last. And again, it's going to give you the same basic information. That's higher up the scale that you go, the more information that these meters are programmed or designed to provide via integration. And this is a more extensive model. It's the same thing. It's going to give us more and more information. And this is an Ethernet flavor integration, and it will do multiple channels. So, Honeywell, E-Mon, Dent, Phoenix Contact, Schneider Electric. Somebody chime in with whether we can sell ABB. But all the different types of meters that Brody Precision can provide to our customers. You need to speak to your sales rep to find out which application, which meter works best for your application, I should say. And the sales guys speak to Frank and I if we need, if we need to get involved. This next slide here is a basic line diagram. This is normally, we don't see this in the building automation world. This is going to the electrician, but I wanted to show, I pulled up an electrical line diagram for a building that we worked with a contractor on. And you can see on the very left, the primary that's going into a transformer. So that's your high tension coming in. On the far left, it's transformed down to 480 volts, and that's where we stick our meter. That is before anything is taken off of the transformer, we have our meter. And if you follow that line to the distribution panel, you will see the 480 volts goes up to all the different panels on each of the different floors of this building. And then it's transformed down again to 208 volts. And you can see that our building is essentially before the very first takeoff, so that we're capturing the entire building load. Now, there's not to say that you can't put a meter on each of these, like each of these little rectangles represents a panel on a floor, electrical panel on a floor, 480 volts or 208 volt panel. You could put a meter downstream down there and just monitor what's going on that particular panel. You could put a meter on a single piece of equipment, and it's going to ask us the same basic questions. It's going to ask us for amperage through our CT rings that we're going to stick around each of the phases. And it's going to ask us for our voltage. And from that, we're going to generate kW and kilowatt hours, of course. So the slide here is for main building installation, but not limited to main buildings. You could, all of us have heard of tenant billing, so it has a lot to do with the electrical distribution of the building. If our panel that's up on the 600 level, for example, serves multiple tenants, that's not really a good usage for tenant billing because that one panel serves two separate areas. So if the electrical distribution is such that each panel or each circuit that feeds an individual tenant can be metered, it's a better application for tenants of billing. But again, it has to do with the distribution of electrical power throughout the building. All right, so all of this that we've talked about previously brings us to this slide, and this is kind of where I wanted to start talking about what we can do as building automation contractors to help reduce the instantaneous load any building uses at any given moment. Over the years, I've discussed with contractors, with end users, the best energy savings that you can do in our field. You know, so if we go all the way back to the 70s when the term was called energy management, right? The best energy savings that you can do for any of your customers is just proper scheduling. That will save them the most money, believe it or not. In the 70s and even today, there's a lot of buildings that just run stuff 24/7. Now, if you turn that stuff off for 12 hours a day, you're reducing the amount of energy they use by 50%. Meaning you don't have to be a mathematician to figure out that there's a return on investment that can be saved, that can be realized just by doing proper scheduling. Problem with that proper scheduling is if I have 15 air handlers and I turn them all off at 6 o'clock at night, at 6 o'clock the next morning when I turn it all on, I probably don't want to turn them all on at the same time. Because when I do that, now my kilowatts are like flying through the roof because I started up all of my equipment at the same time. So there are things that we can do to stagger our startup. In the Honeywell world, our controllers have built-in capabilities to do a staggered start. In the Johnson world, same thing. In CCT programming and in the Cyper and Spider programming, we have the ability to stagger our starts through a command variable. And that will reduce our KW, our energy demand on start, okay? That just makes good sense. There are other energy saving strategies like optimal start. Now, for those of you that don't know what optimal start is, it looks at the start time of a particular air handler, for example, or a zone. And it says, hey, you're 5 degrees out of set point. And the optimal start looks at outside temperature, looks at inside temperature, looks at our start time and calculates through a little algorithm how much time we actually need to start that piece of equipment up before the people actually get there. We may start it up at 6, but the people don't get there till 8. Well, if I'm only a degree out, what optimal start strategies do is say, if I'm only a degree out, maybe I start up at 7:35 or 7:45 because I only need 15 minutes to get that 1 degree back when the people get there at 8. That's what optimal start does. And it saves us a little bit of energy there too. I use the term ratcheting peak demand strategy, okay, to limit electrical usage. And all the slides that we talked about this peak demand, you know, our highest half an hour over the course of the year. And what this does, this software is, you know, this can be done by either reading a meter and the kW, the instantaneous kW, or by counting pulses. But you're essentially looking at what is the instantaneous kW that I'm using, and say if I have a target of, I don't know, 10,000 kW, and no matter what, I don't want to exceed 10,000. If I exceed 10,000, it's going to change my rate. I'm going to go up in utility usage. Just using round numbers here. So my absolute shutdown is 10,000 kW. So the goal is to keep it below 10,000 for any given time interval, whether that's our 15-minute or a 30-minute sliding demand. We're trying to keep our counted kWs, our instantaneous value, below that high limit. And we do whatever we can by reducing instantaneous usage of energy to keep that number down. That's what I mean when I say ratcheting. So when we're in our half an hour of window and we're at 9,000 and man, we're going to be at 10,000. We got time left here. So we start shedding loads, or we start changing the set points of air handlers, or we start doing things to reduce the energy consumption to keep it below 10,000. But then after our interval is over with, I want to go back to normal. So that's what I mean when I say ratcheting. It's an analog value. It doesn't stay the same. It's not heavy-handed. I'll tell you a quick story. When we were programming building automation earlier, the 80s, I'll say, we had to come up with all these strategies through the use of mathematics. And there were many strategies that we had to do to our objective was to keep the utilities down. Well, we started making all of these strides in a very heavy-handed manner. And by that, I mean, we were turning off air conditioners, we were shutting down pumps, we were doing whatever we could to keep the energy usage below that, say, 10,000 kilowatt limit that we had to stay below. The problem with that is that the people that were in the spaces began to get uncomfortable because the temperature rose. It's July, we're shutting off air conditioners, and people were getting hot. So then they wouldn't get complaints from the facilities managers that the utilities were high. There were complaints from the people in the spaces saying that they were uncomfortable. So over time, we came up with more, let's say, not so heavy-handed ways of controlling energy. And some of those things are by doing set point increases, very gradual. And it's built into a lot of, Honeywell has it built into their demand limiting. It's demand limiting, DLC, I think it's abbreviated for. But you're essentially coming up with, hey, we're in a high demand situation here. I want to take my 74-degree cooling set point and bump that up to 77. By doing that, we close chilled water valves, or we shut off stages of DX. And by shutting down or closing chilled water valves, our chillers aren't under such great loads anymore, and they begin to cycle down. So those are some of the less heavy-handed methods that we're using. And like even in the wintertime, if we have electric boilers, we can reduce our heating set point. And it's not forever, it's just while we're in a high demand situation. And that is to keep our instantaneous energy use as low as possible. So one of the things that I always use when I write software is the calculated reset schedules for discharge air. So you use space temperature and you use discharge temperature of the air handler. This works particularly well with modulating service, not so much with heating or cooling. But with modulating service, if I calculated I need to maintain 55 degrees because my space is hot, What I can do is essentially take this peak demand information that we've calculated, because we're getting into a high demand situation, and we can add that number to the tail end of our reset. Do the same thing with chilled water. When we're in a high demand situation, instead of making 42 or 44 degree water on our chiller, we reset that water temperature upwards, and our chillers unload, and we start using less energy that way. The next thing that I talked about is to space temperature set point reset during peak demand periods. And what that is and this works more so for staged control. That's what I talked about with, instead of maintaining 74 degrees in the space, we get into a high demand situation. We start making, instead of 74, we make 75. On a rise in demand, maybe we bump that up to 75 or 76. But eventually, when we get out of that high demand window, we're going to drop it back down to 74 again. And on number 7 here is the chiller temperature set point reset. That's the same thing. If we're doing 44 degree water and we're starting to get to our high kW value, we can impose a numeric value on our chilled water set point to say back the chiller off and use less energy. One of the things that I do for static pressure control, and that would be either for pumps or for, say, VAV air handlers, is you could reset your static pressure set point. Instead of maintaining 1.5 inches on a VAV air handler, if we get into a high demand situation, maybe we lower that number because we're in a peak demand situation. And we want to reduce the amount of energy by slowing the speed of the fan down. Now, that may not make a whole hill of beans with one air handler, but when you start moving that to 15 air handlers or 15 pumps that are controlling pressure through the static pressure reset, it starts to add up. And again, this is happening through the demand interval. And what will happen is it goes right back to normal when we're back into our new demand interval. So you can consider some heavy-handed load shedding strategies if you can get away with it. A lot of our facilities won't allow it. You can't shut the air handler off. The people will freak out, you know. I mean, you can't shut the pumps on a chilled water system down. The chiller will stop and we'll need a manual restart. But there are some things like exhaust fans for certain areas of the building. You might be able to shed loads that way. There are opportunities that you could capture through the building automation system that, and it's intended to be shed during high peak demand situations. And those are considered what I consider heavy-handed load shedding strategies. And then one of these other heavy-handed strategies is something that's called duty cycling. And you can basically take loads that you can shed and shut them off during the course of a half an hour or during the course of an hour. And you continue to shut loads off all during the daytime to prevent the increased energy usage. Not a lot of people are doing duty cycling because of it sacrifices comfort, it sacrifices equipment. You're turning equipment on and off and on and off all day long. That puts wear and tear on the equipment. Something that we need to probably discuss in the pitfalls of some of these energy saving strategies. In the box, your Niagara components in the kit control palette, if you drill down into your energy folder, you're going to see electrical demand limit. You'll see set point load shed, set point offset, shed control, and sliding window demand calculations. that are already, they're software tools that are already built into your Niagara build. And this goes back into the AX world as well as the N4. So these components are available to us. You don't have to program anything. You have to piece it together and apply it to your equipment. But the building blocks are here, built into your Niagara components to do all of these strategies I just discussed. In the Spider world, or the Honeywell Spider world, which is also applying to our Cypher world, our Ethernet-based controllers, we have the electrical power meter, the meter counter, and from there we can develop, again, we can develop kilowatt hours, and we can develop our sliding window of demand limiting. Again, these components are built into our tools. Now, I checked in the CCT and for the Johnson world, and there is no such components at the unitary level or the controller level. I think Johnson intended us to take care of this on the supervisory level. And if that's the case, you would use the Niagara energy components to implement change to equipment and set points on your unitary level controllers. And these are some of the pitfalls. I'm going to round this thing down here. A lot of times we install these energy meters into buildings, and other than the utility bills that have come in from our electrical utility, whether that's PSE&G, PECO, Delmarva, whoever the utility is, nobody really has kept an energy profile of what you're putting a meter on. That's what I mean when I say baseline. What was the energy usage prior to us implementing these changes, these electrical change, these strategies that were employed? You have to know basically where you are before you can start assessing savings. Now you can calculate certain things, but without the use of a baseline, it's difficult to predict any kind of savings that these strategies can yield. I talked about the proper location of the energy meter to capture the entire building electrical profile. I've seen guys put in meters downstream just they didn't know any better. And you didn't capture the entire utility meter, it only captured part of the building. So that messed up. Well, why doesn't my meter read what the utility meter reads? I'm not even close. Well, that's because you didn't capture the whole building. Seen that happen a bunch of times. So we need to be careful about where we're installing our meters. So when we install this meter, is all the equipment functioning? We could go into our facilities manager and say, we're going to put a building automation system in your building. We're going to save you all kinds of money through our energy saving strategies. We're going to control your equipment. You're going to have better temperature control. You're going to have better energy savings. And a lot of times the energy bills start going up, not down. And that's because the contractors that go into these facilities start finding all of these pieces of equipment in various stages of disarray. Some equipment isn't running. Some equipment, you've got a 2x4 stuck in the outside air damper. All kinds of different things will cause the building to now consume more energy. And your facilities guys start looking at you like, this thing was supposed to save us money. Well, what you did is you got them a better working building. And sometimes that costs money because they don't know any better. I know over the years, a lot of facility managers, they don't have a really good idea what's going on in their building. They respond on what's going on in their building based on complaints and phone calls that are coming in from the absence of control or the absence of lights or some other complaint. That's what I mean when I said, is all the equipment functioning? I've had contractors that go into buildings and they start getting air handlers working again, and that's going to make your energy bill go up. I mean, if that fan has not run in a year because nobody knew it was off on overload, and the building automation guys come in to capture it as a potential, now you're going to spend more money. And he didn't even know that the air handler was off. See that happen a lot. During the time after the meter was installed, has any equipment changed? This is another problem that we run into. Okay, well, that air handler is no good anymore. We're going to put in new pieces of equipment, or we're going to put in two pieces of equipment where there was one, or something has changed the reason that the energy profile will be altered because the equipment is not like for like. You're not comparing an apple for an apple, because now new things have been installed and they're no longer the same. I've seen guys replace centrifugal chillers and they put in recips, or they'll put in air-cooled chillers or something like that. Well, that's not an apple for an apple. It may be from a cooling standpoint, but from an energy standpoint, it's not. Sometimes building profiles change based on the way that they operate their building. So we no longer have a wide open space. We have a tenant fit out and we're now occupied. Well, because we have a tenant fit out, our energy bill is going to go up because we're using more energy because the floor is now occupied. So these are all things that you need to consider when you're putting this stuff in. It's not just reading information off of an energy meter and saying, hey, look, I'm going to save you money. You have to have a little bit of knowledge of what's going on in the building and things to keep your eyes open to over the course of the year, especially if you're trying to sell this thing based on energy savings. Now, all of the things that I just talked about, they're going to add engineering hours to your time. Now, that's all fine and good if it's built in to your costs when you're going to your customer and you're going to say, hey, we're going to save you some energy. We're going to do better control. We're going to do better utility management. If you build that into your engineering hours. But a lot of times we start doing these things and it starts adding to the labor hours on your engineering. And you may run into cost overages that way. So just something to keep aware of. And I don't know about you guys, but when I create the wheel or I create an energy strategy, it goes into my library and I don't have to reinvent that wheel later in life. I have it stored away, something that I can use again, and I don't have to spend all that upfront time on the next time I apply that application. And the last thing that I wanted to talk about was for every Niagara build that goes in, you're getting 25 analytic points as part of that build at no cost and no additional cost. So I would strongly recommend that you use those analytical points for some of the pieces of information that you're pulling out of what we talked about today. That is KW, kilowatt hours, demand, peak demand, when it happened, that sort of thing. Does anybody have any questions? We're about at an hour here. I wanted to wrap this up.